there, I'm Victoria Miller, and I'm here to talk about harnessing the wind and engineering challenges and solutions in blade design. The largest wind field I've ever seen was at the base of the Sierra Nevadas, and it was the Tehachapi Wind Project. It covered 800 square miles and contained 3,400 wind turbines to generate 700 megawatts of electricity for the state of California. It was really quite a sight to see. The wind energy is a popular renewable energy because it doesn't cause pollution, it doesn't impact air and water with chemicals, fossil fuel pollution, and so forth. And it comes in three basic categories: the onshore or land-based systems, offshore system, and distributed wind energy. So when we think about land-based, those are going to be towers that produce about 4 megawatts of capacity annually. Offshore towers tend to be much larger, producing somewhere between 8 and 15 megawatts annually. And the category of distributed wind energy covers small things, like things that would be mounted or turbines that would be mounted to houses or maybe supply small communities, possibly a wind turbine that generates power for a well in a remote or rural location. So, as with most engineering feats, size matters. The hub heights tend to grow larger over time, as well as the rotor diameters tend to grow larger over time. Nameplate capacity also increases. Nameplate capacity refers to the amount of energy generated by the wind turbine under ideal conditions. So we become more efficient and larger. How does an offshore or an onshore wind farm work? Basically, wind turbines are connected by cables. The power travels down the cables, through the cables to substations where it is then uploaded to the electricity grid. The offshore systems can have floating wind turbines that can be gathered before storms or brought in for service. They have jacketed or monopole systems that are fixed in areas with water of less depth, and they are all connected by undersea cables that feed into substations. The offshore turbines tend to be much, much taller, and so they are generally the same height as the Washington Monument, hence the panel on the left. These wind turbines components are similar across onshore and offshore. Land-based turbines are mounted to platforms and mounted that are affixed to the ground, and the cables that carry the power run underground. The parts follow the simple term of tower, which supports the nacelle, and the nacelle is connected to the rotor or hub, and blades affixed to the hub. Inside the nacelle, there are lots of parts. The average wind turbine has 8,000 parts, which is simply a staggering number. First and foremost, the yaw and the yaw drive, located towards the bottom of the panel on the right, allows the wind turbine to physically rotate and face oncoming wind. The pitch system allows the wind turbine rotor to tilt and meet the wind in the correct direction, at the correct angle, if you will, for improved efficiency. Inside that nacelle, there are shafts, gearbox. The mechanical energy is converted to electrical energy through the generator, and the electricity then passes through the cables down the tower and connects to systems. Domestic onshore wind manufacturing, where do we get all of these parts? They tend to be manufactured in the central United States. There is a romance with just-in-time delivery, which makes it cost-effective to make wind turbine parts near their location or destination and be able to ship them relatively quickly. There isn't anything more expensive than trying to ship very large things from overseas or store very large things for long periods of time. So this industry moves a little more quickly. Many of the blade components, tower components, and cable systems are manufactured locally, and the plants are up and working. There's several more that are in the pipeline to support future needs. The difference between the onshore wind component manufacturing and offshore is simply a shipyard. The offshore wind manufacturing components include vessels to carry crew members, vessels to oops, assemble wind turbine or installation, service those existing wind turbines. So it is building a fleet of ships that can support this industry and allow it to function. As well, the second component is manufacturing of undersea cables, which the largest manufacturing for undersea cables is in Georgia, and there's another plant in Maryland. So we get all of these parts, all 8,000 parts or so. Significant number are still sourced from overseas: Mexico, Canada, Germany, Denmark, and we assemble wind turbines. And what attracted me to this project on blade design was, as a biologist, I am always excited to learn about the application of the natural world to engineering. Hence the picture of the cicada wings in the lower left-hand corner. We take our best ideas from nature because natural selection has brought us the benefit of a million or millions of years of experience to the table. So we look to the natural world for inspiration and ideas, proven designs. So we take into consideration aerodynamic design, bend twist distribution, the construction of what's called a flat back airfoil, carefully selected materials, taking into account the number of blades, and then some features that improve power output and decrease noise called tubercles or serrations. So when you evaluate the movement of the rotor and the spin of the blades, the speed of the wind traveling over those blades will vary. Near the rotor, the speed is much lower, hence the blue and the green colors. And further from the center of the hub rotor, the distant end of the blades, the color is red to indicate a much greater wind speed. There's a considerable amount of math that goes into designing these systems and coming up with this information, and it is out of scope for this particular presentation. On the right-hand panel, there is a representation of load. That is the entire length of a blade, a wind turbine blade, and the greatest load, shown in red, yellow, and then towards the green, is experienced in the middle of the blade, with the root where it bolts to the hub and the tip having the least amount of load. So take that into consideration in designing these blades. The basic blade design is something called an airfoil, and across the length of the blade there will be a multitude of airfoil dimensions. The leading edge of the blade is the wider end. The trailing end of the blade is the narrow end that comes down to a point in this particular cross section. These are modified to allow for differences in shapes. So an airfoil on a wind turbine blade is a specifically shaped cross section designed to generate aerodynamic force or lift when the wind flows over it, causing the turbine blades to rotate. So here on the right-hand panel, you can see the force or lift over top of that airfoil design. A typical blade will use multiple different airfoil shapes along its length because the wind speed will vary along the span. So different airfoil shapes, and they serve a purpose. But to support them, the interior of that blade needs mechanical structures. And those are, if you look in the left panel, the shear webs, and they're usually two, sometimes more, that span the distance, the void, if you will, inside the blade. They are affixed or abut something called a spar cap on both the top and the bottom of the blade that provides reinforcement. And there are also additional panels called sandwich panels that strengthen that blade. All of this is a staggering design feature. Lots of experiments with modeling different shapes and outcomes in noise and power production and longevity. To this design, a twist has been added. And you can compare from the left to the right a blade that doesn't have a twist to a twisted blade. That twisted blade just appears to have a little more curvature to it. And what that does is it produces a blade that is adaptable and resilient. When the wind blows at maximum force, maybe it exceeds the design specs for the wind turbine blade, or it's right at the outer limits. That blade is going to bend. In some of the earlier designs, it would bend and crack or shear or break down. But in this bend and twist design with the flat back airfoil, it is able to bend to the point that it's going to twist in the wind and deflect some of that force, and it allows for longevity of those blades. So you can see that the airfoil has a specific shape up at the top of that panel on the left-hand side. It has a flat back, and it is designed to slow those blades down in concert with both the blade pitch system and the braking systems available in wind turbines. So there's mechanical braking as well as some aerodynamic braking systems. So this all comes down to what this blade is constructed from, longevity in terms of how well it will hold up. The most popular material is called the carbon fiber reinforced polymer, and that is because it is very high strength and it exhibits some really wonderful elasticity that allows it to move and flex and deflect force. Some of the less expensive or less critical areas can be sheeted with fiberglass. Of course, fiberglass is much less expensive, but the gold standard is what's called the aramid fiber, which is very similar to Kevlar. It is very long lasting. It is resistant to damage. It is produces the least amount of noise, and of course, it comes with a much larger price tag. So just for fun, on the right-hand side, there is a wind turbine blade being constructed out of something called laminated veneer lumber. It's supposed to be 262 feet long, and it is a project between a lumber company in Finland and a blade company in Germany to create entirely recyclable wind turbine blades, and it will be coming to market here shortly. Just to mention, the reason most wind turbines contain 3 blades is because it is the sweet spot between the vibration problem that comes with fewer blades and the additional weight, mechanical stress that comes with hosting a greater number of blades. So our onshore and offshore systems use 3-blade wind turbines for that reason. And just for fun, to the far left and the far right, I've shown you a couple of what are called vertical axis wind turbines. They are designed for distributed wind energy projects, so they generally operate alone to support small power needs, and they have these really fabulous shapes that generate energy. The last feature of the blade I want to talk about today is the bio-inspired edge adaptations. So the humpback whale has these wonderful bumps on the fronts of its fins that allow it to dive in the ocean and hold very sharp angles with very little energy. And this adaptation has been brought to market for the leading edge of wind turbines to reduce drag. And that, of course, improves power output. The second feature, the inspiration came from the feathers of an owl. As you notice with microscopic examination that there are tiny serrations or notches in these feathers, and that reduces drag, reduces noise, again, improves power output. So the humpback whale and the owl have both brought to wind turbines some wonderful ideas for improvement in the future, and some of these can be aftermarket add-on or bolt-on products. So the safe and efficient operation of wind turbines relies on blade design and their materials, aerodynamic shaping, selection of materials that will hold up to stress and high winds, in concert with aerodynamic braking systems and yaw control that will allow for optimal location and positioning of the nacelle. Mechanical braking as the emergency backup when things get going perhaps too fast, and high gusts and climate change and weather pattern differences, and in advanced control systems where algorithms, weather predictions, modeling, and systems allow for remote operation of these turbines for optimal conditions. Thank you for watching this presentation. Please let me know if you have any questions.